Today's video is how to calibrate a basic analog oscilloscope like this 25 megahertz Heath 4552. Now when you're going to calibrate an oscilloscope, there's a kind of a checklist you need to kind of start off thinking about. One is everything working properly on the scope in the first place. You really can't go ahead and calibrate it if there's a portion of the scope that's not working right. And are all the controls clean? When you adjust the pots and things like that and the switches, if they're dirty, you really need to clean those first before you begin your calibration. And do you have all the equipment required to do the calibration? And that might mean, a high voltage probe. It may mean some calibrated signal sources and things like that. So you've got to make sure you've got all the equipment available. And most important, do you have the service or calibration manual or instructions? Even a very basic scope like this, we'll see, can get pretty involved if you want to do the calibration properly. There's a lot of adjustments and a lot of them interact. And if you don't have the instructions, you run the risk of doing more harm than good in trying to just make a quick adjustment on one parameter. So we're fortunate to have the manual and all the documentation for this particular scope. The scope was actually made by Pintech, but was private branded by Heath as well. It was interesting enough, if you look online, this same scope is still available new, even though this one here is from 1989. Well, anyway, the manual includes all the instructions on how to use the scope, but also has all of the maintenance and adjustment instructions, all of the adjustment locations on the three circuit boards or three circuit boards that are inside, as well as a complete schematic. And really, all of these things are invaluable, as we'll find out that even a very simple scope like this can get pretty involved in doing the calibration properly. Now, I've previously gone through the scope with all the controls to be sure everything is working properly. So next thing we do is take a look at the manual and go through the required equipment list. And I've got basically everything that's here. A couple of minor exceptions. They ask for a 50 ohm 1 megahertz square wave pulse generator that's got a 1 nanosecond or less rise time. Now the generator that I have has got about a 2 nanosecond rise time, but for this scope, since it's only 25 megahertz of bandwidth, I think what I've got should be close enough to get the scope working. And everything else we basically have got covered. So with that, we can get started. And of course, one word of caution before we start taking the covers off here is that with any analog scope that's got a CRT, there are high voltages present. They could be 1500, 2000 volts, or sometimes as much as 10 or 12,000 volts or more. So if you're not comfortable with it and you don't know what you're doing and you don't want to risk it, leave it to a professional to go do, because there are dangerous, lethal voltages inside these scopes. But the first step is to check power supplies. Now in this case, there's a single 12 volt supply that is used as a reference for all the other supplies. So we're essentially going to measure and adjust this single 12 volt supply and then just check the minus 12, plus 5, and plus 145, and then the 2 kV for the anode in the CRT. Okay, the manual says that we look on pin 4 of this connector here, and we can see that we've got 11.94, and the spec is looking for 12 volts plus or minus 0.05. So we're really close, but we do want to make an adjustment. Of course, you always want to use insulating tools when working on something like this, especially anything with high voltage. So let's probe that voltage here and get my adjustment screwdriver down into the trimmer down here, and we can make an adjustment on this power supply. Let's see. Need to go the other way. And we'll get that adjusted to right at 12 volts. So now our main 12 volt supply is adjusted. So next we check the negative 12 volt supply, which will be on pin 5. That's minus 12.01. That's got to be within plus or minus 200 millivolts, so that's fine. We'll check pin 3 for the 5 volt supply. That's got to be within a quarter of a volt, so that's fine. And we'll check the 145 volt supply on pin 7. Oops, how about 7? And that's 146, and that's got to be within plus or minus 5 volts. So the rest of those lower voltage supplies are fine. Next we can look at the 2 kV voltage carefully. So we'll use this 100x high voltage probe along with the meter to measure the minus 2100 volt supply. very carefully, one hand, and go and touch the test point, and we're reading minus 2,168. That's reading slightly high, but the manual says to make the measurement with a voltmeter that's got an input impedance of 10 megohms, and this one is 1,000 megohms, so it's a much lighter load. So I'm not too worried about the fact that I'm just slightly high on that supply voltage. So with that, the power supply checks are done, and we can move on to the next section. So on to the CRT circuits. The first adjustment is for the min and max intensity adjustment, and the instructions say to turn the intensity to the 9 o'clock position, and then make an adjustment so that the trace is just barely visible. So I'll just dim that out so it just goes away. It may not really be visible even on camera. The next is to adjust the maximum intensity, so we turn that to the 3 o'clock position here now, and adjust the other trimmer, that's back here, until that the trace, when it's properly focused, occupies no more than 1/3 of a minimum gradical. So it's just kind of doing that by eye. It's just kind of an approximate thing. Right about there is probably good. This gives us a good range for the intensity. So that's now adjusted right. All right, the next thing we want to adjust is astigmatism, and the idea here is we want to go to XY mode with nothing at the input, adjust our focus for a tight spot, and then make an adjustment to the astigmatism pot to make that as kind of as circular as possible. And it looks like that's right about there. The next is the trace rotation, and sometimes you'll need to adjust this after you put the scope on the bench because it is affected by the Earth's magnetic field, but we'll just adjust that and get it close for now. So next we adjust the retrace brightness. The retrace is essentially the beam being swung back to the beginning again. You should not see it at all. And when it's not adjusted right, let's see, you can just barely see a trace flying back down here if you look really carefully. I don't know if you can pick it up on camera or not. So we'll adjust until that goes away. Check a couple of other horizontal time-based settings and be sure we don't see a retrace. And then we're okay with that. Well, the next step is to go on to the vertical amplifier adjustments, and there are 8 steps. We have to check the step DC balance, the ×5 magnification DC balance, the variable DC balance, the add mode DC balance, the sensitivity calibration, the ×5 gain calibration, the vertical transient response. And then it also have to do the input attenuator adjustments, and there's a couple different methods we can use here before moving on to the trigger circuit. So we can see we'll spend a lot of time on the vertical calibration. Now to check the step DC balance, we ground the input, we'll put it on channel A, and go through the most sensitive volts per division settings. Now if there was a balance problem, we'd note a shift when we go to each setting here, and channel A looks okay. Let's go to channel B, we'll ground that input and do the same thing there. So it looks like the step balance is okay on both channels. So next we'll check the DC balance for the ×5 vertical magnification. So we'll start off on channel A, again with the input grounded, pull the, in this case we pull this knob to go to the 5 times mag, and we noted that we didn't really see a noticeable change in the vertical position. Switch to channel B and do the same thing. So it looks like the DC balance for the ×5 vertical mag is okay. Now of course if the DC balance for any of those just tests that we did indicated a problem, there's an appropriate adjustment to be made on a trim pot on one of the boards. Now to set the add mode DC balance, we first set the position of the channel A trace in the center of the screen, then switch to the channel B trace, move that to the center of the screen, and with those both set to center, we go to add, we see very little shift, and I see a slight shift in the negative direction, so we'll make an adjustment on that. Alright, so we'll make a slight adjustment to that pot to put that right in the center there, and now I see no appreciable change when I switch between A, B, and the add mode. Okay, the next thing to set is the vertical sensitivity adjustment. So we set the signal generator to a 1 kilohertz 50 millivolt peak-to-peak signal, going into a 50 ohm terminator here. We set the time per division to 1 millisecond a division, DC couple the input, and set the input to 10 millivolts a division, and I'm just going to center this down here so I can see everything going on. Now, of course, we want exactly 5 divisions here, and I've got slightly more than 5 divisions, so I'll make an adjustment on that trimmer. I might have to adjust the vertical position here, and so I can get exactly 5 divisions on the screen. Looks like we're right there. And we need to repeat that for channel B. Okay, moving that signal over to channel B. So the vertical mode to channel B, DC couple it, trigger on channel B, and let's set that to 10 millivolts of division, and let's see where we are. And it looks like this channel is very good. I've got precisely 5 divisions vertical deflection, so there's no adjustment needed on channel B. Now, according to the instructions here, once we complete that adjustment, all of the other volts per division positions should be calibrated to within plus or minus 3%. They use precision resistors in the attenuators, so we're just making one gain adjustment to set everything right. So we should be good to go with that. Now, of course, we can validate this by going to a couple of different vertical positions. Say at 20 millivolts of division, I should have 2.5 divisions here, and we do. If I go to 50 millivolts of division, I should have exactly 1 division of deflection, and I do. And of course, we can change amplitudes and go do that, but no need to do all that on camera. But the next step is to set the gain for the 5x magnifier. So I've adjusted the input signal down to 10 millivolts peak to peak using an external attenuator here. We're still at 10 millivolts of division on the scope. I see 1 division here now. If I pull the 5x multiplier out, I should see exactly 5 divisions. I'm actually seeing ever so slightly more than 5 divisions. So we'll go in here and make the adjustment on that to bring that down to 5 divisions here. So just down the other way here, right about there. Let me adjust the position here and see. There we go. So that one's set. We just need to repeat that for the other channel. Okay, just repeating this adjustment for channel B. And it looks like we're right there. Of course, it goes without saying that all of these adjustments on the vertical gain need to be made with the vernier adjustments for the channel rotated clicked into their calibrated position. The next are probably the trickiest adjustments to make, and these are for the transient response for the vertical channel. So we basically have to put in a very fast 1 megahertz square wave at a 10 millivolt per division, adjust for 6 divisions. And what we're trying to do is adjust literally 6 controls that all interact to try to obtain a waveform that looks like this. Good straight edges and just a little bit of ringing on the top and bottom of the waveform. And we can see that if we look carefully at the waveform here, I've got a little bit of sag here, a little bit of sag here. So I do have some adjustments to make. But given that there are 6 different controls that interact, it's probably going to take a while, so we'll do this a bit off camera. Alrighty, so after about 10 or 15 minutes of twiddling with those 6 adjustments, we've got a pretty decent looking square wave here. Got rid of a lot of the anomalies at the edge of the rising edge and the falling edge of that waveform. Now, of course, we've got to repeat that for channel B. Alrighty, just about on the final adjustment here for channel B. And that last final little tweak, we can get rid of that overshoot that's occurring and make that a nice flat looking square wave right about there. Tweak that a little bit more. There we go. So again, that's a pretty tedious adjustment to get the transient response right for both these channels. And this is just a 25 megahertz scope. For higher bandwidth scopes, these adjustments will be more critical and more numerous. And the next step is to adjust the compensation for 2 ranges on the volts per division scale, on the 1 volt per division and the 0.1 volt per division. And there are a trimmer cap for each one. We put in a couple of kilohertz square wave and look for that compensation waveform. And we want to adjust that so we don't have any overshoot like we have there, and we don't have any undershoot. And looks like that's just about perfect for that range. So we'll do the 0.1 volt per division range here, and then the same thing for channel B. Now the next step is to make an adjustment to the input capacitance at a couple of different volts per division settings. So the reference setting you start from is at 20 millivolts a division, and we basically set up a high quality pulse generator into a probe and properly compensate that probe to get a nice flat response right there. And now the idea is, as we go to the other two positions, the 0.2 and 2 volts a division, we should have the same, we shouldn't have to adjust the probe compensation. And we can see here that we're not properly compensated, so that says at that volt per division setting we don't have the same input capacitance, so we need to make an adjustment on that. Okay, so leaving the probe alone, we'll adjust the input capacitance at the trimmer on the board and try to get that to be just about perfect here. Take a little bit of tweaking, and that looks pretty good. Alrighty, so just finished making those adjustments for channel B through the couple of ranges, so that finishes up the vertical section and vertical adjustments. Okay, the next adjustment is to the trigger offset. We apply a 1 kilohertz sine wave to the input, AC coupled, to make sure that the signal is centered on the screen. We'll adjust the horizontal position so that we can see where the waveform is being triggered. Set the trigger control to its mid position and adjust the trigger offset control until the waveform basically starts right at mid scale. Right there. So that will ensure that the midpoint on the trigger level is midpoint on the screen. Okay, the last adjustment for the trigger on this particular scope is the alternate trigger. So I've got a 1 kilohertz sine wave, a 10 kilohertz square wave per the manual applied to channel 1 and channel 2. And we put the scope into alt trigger mode. You can see those signals are actually not being triggered right, so this circuit actually does need adjustment. So we'll go in here and make that adjustment here. And now we can see both those waveforms are triggering properly. So we're finished with the trigger section. The last section to adjust is the horizontal time base accuracy, and that needs to be done at 2 different settings. There's 2 different controls for that, as well as in the ×10 horizontal magnification. So the first thing we want to do is ensure that the variable control is all the way fully clockwise and in the calibrated position. Next we apply a time mark signal to the input. Start off with a 1 millisecond period for that time mark signal, and also set the time base to 1 millisecond per division. We can see from the instructions here that what we need to do is adjust the control for this, and also adjust the position kind of back and forth so that we can get all of the pips effectively to line up with vertical gradical lines. And there's a special note here to pay particular attention just to the center 8 divisions. And the reason for that is that the sweep voltage can often be a little nonlinear at the very edges for the last 2 divisions. So we're really not going to pay too much attention for the pips that are hitting the edges of the gradical, but just the center 8 gradicals here. So if we look carefully, I've got the position adjusted, so I've got a pip lined up right in the center. And as we go away from center, we can see that we're gradually more and more off of those pips. So we certainly need to make an adjustment. So I've got the screwdriver in the pot here, and we'll make an adjustment and pull those things around, readjust our position here, and we'll keep iterating back and forth here until we get those things to line up on those center 8. We're getting really close here now, just a little bit off at the other end here, so I'm going to do just a little bit more, and this will probably be as close as we'll get this 25-year-old scope to be. Alright, the next step is to change the period of our time mark signal from 1 microsecond a division, or 1 millisecond a division, down to 1 microsecond a division, and change our time base to 1 microsecond a division here. And then there's an adjustment we can use to clean this one up, and this one is actually pretty close. I don't know that I need to touch it up a little bit, just a little bit off at the edges, but not much at all. So we'll see if we can tweak that just a little bit. I've got a non-conductive adjustment tool in that final capacitor here, and if we tweak that ever so slightly, and looks like we're probably pretty good right there. I've got all the pips kind of lining up with the graticles there. So that should be the final adjustment for the normal ×1 horizontal time per division. So next we do the 10x mag. So for the 10x mag, we want to change the time interval mark to 0.1 millisecond interval, and we set the time per division down to 1 millisecond, and then pull out the ×10 mag. So with the ×10 mag pulled out, we can now see that waveform. We can adjust its position, and we look carefully here. We can see that we're lined up on the center here. We're just ever so slightly off, so again a minor adjustment to get this one going. Okay, with the adjustment tool in the trim pot here, we can adjust this one to try to get all of those pips lined up there, and boy, that looks like that's again pretty darn close, as close as we're going to get here probably on a again a 25-year-old scope. So with that, looks like we've got the calibrations pretty much wrapped up on this scope. So with that, just a couple of comments and disclaimers. I'm not a calibration professional. I'm more of a hobbyist when it comes to this kind of a thing. The equipment that I have here that I'm doing the calibration on this old scope with is not NIST traceable or anything like that, and some of it I'm making do with the best that I have, as opposed to using exactly what was specified in the documentation here. So, and every scope is different, but there really is no substitute for having the proper instructions for how to do things. You may have noticed from, like when we did the vertical section, that there were a number of adjustments, at least 5 or 6 different places to make adjustments to fine-tune the transient response of the vertical channels. That's something that's not going to be very intuitive and easy to figure out just simply by looking at the adjustment controls that are on a board. Some of the things are fairly straightforward, some of them are a little bit tricky, and some of them require making settings, in a couple of different areas and making adjustments. So you really wouldn't know that without having the proper documentation for the scope that you're working on. But with that, I just wanted to give you an idea of what's involved in calibrating and adjusting a fairly simple scope like this. And you might imagine that higher bandwidth scopes or more sophisticated oscilloscopes with more features are certainly going to be more involved. Some of the the higher performance Tektronix bench scopes that I have here, the calibration section is dozens and dozens of pages long, 50 or 60 pages long to do the calibration properly. So I hope you can appreciate what's involved when someone asks to have a scope calibrated. There really is a lot involved to do it properly and do it right. Anyway, thanks again for watching, and I sure hope you enjoyed the video. Comments are always welcome. Thank you.